All right. So, that's right, I guess. Oof. All right. We got some lag going. Cool. Okay, so okay, we had a full screen. Why? Oh, I'm not in full screen. Sorry, you guys. Technical difficulties. Make this window smaller. Ugh. Okay. So I'm just going to go through some of the problems from the practice exam so that we have a little bit of practice with it. No pun intended. So let's start off with number 13, which is just reviewing some isotopic notation. So we have our isotopic notation. We always have the chemical symbol, the number of protons, and the atomic mass, right? So the most confusing thing about this for students, I think, generally, is that these guys are not in the same place as they are on the periodic table, right? So on the periodic table, you have the number of protons. Sorry, I got some serious lag happening here, guys. So on the periodic table, we have the number of protons, or Z, is going to be in the top left-hand corner, right? I'm pointing at that. Now you can see it. So I think that's the most confusing thing, right? Is that this guy is the number of protons, and this guy is the number of protons plus the number of neutrons, right?
And then to find the neutrons, we would just subtract the protons and the weight, the atomic weight.
Yep. So
that's what I can never remember.
So this is the atomic mass, right?
Right.
What's on the periodic table, that's the atomic weight.
Right. So I know that, but it's the finding of the neutrons that I always get confused about.
Yes. So so for example, let's say we had carbon. Say we have this guy, right? How many neutrons does that guy have?
6, but it's not from this that I get confused. It's from it's from the mass. Like, say it's on the periodic table and we have the weight, the atomic weight, and the atomic number. That's where I get confused about.
I'm not going to ask you that type of question.
Okay.
Yeah. Yeah.
You'll just give us things like 30, like on the question 13, it says 33 protons, 41 neutrons, and 33 electrons. And we don't really need to know about electrons. It's just to
That's correct.
throw them in there, right?
Yeah, so there are different parts of the electronic structure that matter when you're talking about different things, right? So when you're talking about an isotope, right, you need to know about the number of neutrons and the number of protons, right? The number of protons tells you about the element that you're dealing with, and the number of neutrons tells you about the particular isotope, right? But the electrons don't matter.
Thank you.
Yeah, so, I'm sorry, I gotta pull that up again. So, oops. So we have 33 protons, right? So what's our symbol gonna be?
AS.
Arsenic.
That's right. So our symbol will be arsenic, right? Our atomic number, or number of protons, is 33. And our number of neutrons given are 41. So 41 plus 33, 74.
Yeah.
So that's what we put up there. Coolsies? Cool. I think the harder version of this question, and the one that you guys struggled with a little bit on the quiz, was when you're given this and you're asked to find the number of neutrons. I think that was, some people had some difficulties with that. So yeah, you can literally just think about taking this number and subtracting this number, right?
Like, just maybe like a helpful tip, the way that I think about it is, because they're different in the periodic table in this, but the smaller number is always the number of protons.
Yes. True.
And then you subtract the smaller number from the larger number.
Yep. Yeah, because you can have a negative number of neutrons, right? So, as long as you know that it's subtracted, and as long as you know that this is not the number of neutrons, right? And I think that's the thing that a lot of people accidentally do, right? So they'll put 33 protons and 74 neutrons, right? Which is not the case, because this is protons plus neutrons. Cool. Any other questions about those? Pretty straightforward. Cool. So, I think there was some questions on the quiz that gave you like, what is the identity of an element or ion? Oh, you guys can't see me, sorry. With 46 protons and no, let's do something more reasonable. 43 electrons.
Is that palladium? Is that how I say that?
Mm-hmm. Palladium. Yep.
Palladium. Okay.
Yeah. So again, this is another example of when you're looking for the identity of an element or an ion, right? That's indicating that you're looking for oops, not PB, PD, sorry. You're looking for the chemical symbol or the chemical name, right? Palladium? I think I spelled that right, right? So if I asked you for the ion notation, right? What would the ion notation for this guy be?
Would it start off with PD first?
God, why can't I write the letter D? Sorry. PD, there it is.
And then is it just the Roman numeral after that for the ion notation, or is that something different?
That's for the ion name.
Gotcha.
We'll do that one next. So for the ion name, we can just do that now.
Be 46 on the bottom. Sorry for the notification.
So what would the charge be here?
Plus.
What is it?
Plus. 2 plus.
2 plus?
Wait.
Would it be +3?
Yes, it would, right? So you have 46 protons, which means that you started off in a neutral atom having 46 electrons, right? In your ion here, you've lost 3 electrons, which means that you have a +3 charge, right? And what would my Roman numeral be?
PD 3.
I, right?
Yeah.
And then the ion part, sorry for all the parentheses, is optional here, right? So if you were to give me the ion name and include ion in the name, that would be fine for this one. But if you didn't include it, you wouldn't be wrong, right? You do need the parentheses, though. So once we get a little bit farther along, we can kind of start ditching some of the parentheses, but for now, I want to see them. Okay? You want to do another example of one of these?
All right.
Go ahead,
So
Sarah.
that would be, with the ion, that would be palladium ion 3.
Palladium 3.
Okay, but you said you wanted to add the parentheses for the 3 or for that ion?
So what I'm saying is the way that this reads is palladium 3.
Okay.
Right? And the reason why we don't need to say palladium plus 3 or palladium 3 plus is because all metals have a positive charge when they're made into ions, right? This is another super important thing to keep in mind. So ions of metals will always have a positive charge. They will never have a negative charge, right? Who has a negative charge as an ion?
Non-metals.
Non-metals, exactly.
Non-metals.
Do we need to memorize the 7? Oh, for the diatomics, sorry, you came in a little bit late, Jesse. We said no, you don't need to know the diatomics. We're going to talk about it in chapter 4. Any other questions so far? We do another one of these?
I want to do another one of these if that's possible.
Totes?
Me too.
Me too.
Okay, so let's say oof. Sorry, guys. That's the other reason why I can't do synchronous lectures for the entire semester is literally sitting in this chair is killing me. There's a big part of the semester that I'm going to be conducting from bed.
Professor,
Yes.
Have you ever tried to make it a stand-up desk for you?
when
When I was pregnant at work, we put my desk up literally like on boxes.
So that's a great idea, but the desk that I have would just make it a little bit weird. So, oh, you guys can't see. Oh, you can't see me. So like, I have the TV up here, and then my workstation right there, right? So it's like, it's not really how I'm like I might be able to work up there, but it's just hard. And having a place where I can set up the arm.
Yeah.
So yeah.
That was my savior, is that I could stand up and like do
Yeah.
my work because I couldn't sit.
Yeah.
Fine.
Yeah, I get that. So, no, and I actually have a standing desk in my office because of that exact reason. I hate sitting down. I'm not a fan. but yeah, it's in my office, which is so close yet so far. All right, yeah, chat action. Okay.
Is that Br minus?
So 35 protons means we have bromine, right? So our chemical symbol here is Br.
And you gain 1 electron.
And we gained 1 electron. So it would have a minus charge, right? Now again, if this is easier for you to understand, do it. That's fine. That's fine. I wouldn't mark you off for that, right? But I think you should be comfortable, hopefully, seeing this by this point, right? Generally speaking, the ones are implicit. We don't write them. Anything higher than 1, we do write. So what would the ion name be here?
Is it bromide?
Mm-hmm. Right, so we take the ending, which is bromine, and we take the ending off and we stick an IDE at the end, right? And again, depending on which ion you're looking at, we stick the IDE in different places. But my rule of thumb is if it sounds right, it probably is right, right? So for the oxygen anion, what would that be called?
Oxide.
Oxide.
Died.
Mm-hmm. For the sulfur anion?
Sulfide.
Sulfide, yeah. So I think that these are at least a little bit intuitive because you've probably heard them before. So if it sounds right, it probably is. Questions about that? Let's do one more. So let's say we have who dis?
Chromium.
Chromium.
Chromium,
Chromium.
right? Which
Sorry,
has
chromium.
a chemical symbol of Cr. Right? And what is the charge?
Plus 2.
Cr2 plus.
It's 2 plus, right? So we'd write
Roman numeral 2.
Roman numeral 2, exactly.
So am I catching on that when we're going in, like when it's a negative 1, 2, or whatnot, we kind of go into the ides and stuff, and then when it's a 2 plus is when we have the Roman numerals?
Okay,
Like
so
up is Roman numerals and down is the ides?
this is only for transition
Oh,
metals.
okay, sorry.
No, that's okay. And post-transition metals.
Okay. Okay.
So the Roman numeral does not need to be given when you're dealing with, say, group 1 or group 2 ions, right? So the ion name for potassium, for example, K, would just be potassium ion, right? No need for a Roman numeral because the Roman numerals are given for the transition metals or the post-transition metals because they can have different charges, right? Because they have all those extra electrons in their belly, right? They can have, they can lose different numbers of them, right? But here, when you only have 1 or 2 valence electrons, you're only ever going to make one flavor of ion, right? Here it's going to be a positive 1 in group 1, and here it's going to be a positive 2 for group 2. So we don't need to write the charge because we know what the charge is going to be, okay? There is another thing that we'll talk a little bit more about probably on Monday, but you don't need to know for the exam. And that's that there are a couple of transition metals or post-transition metals that have the same charge always. And so you'll see occasionally there's a handful of transition metals that won't be accompanied by a Roman numeral. I personally would much rather you just always give me a Roman numeral for one of those guys. But just so you know, if you see silver, zinc, and aluminum, never change. They're always 1, 2, 3 up the stairs. Okay? So silver is always +1, zinc is always +2, and aluminum is always +3. They never have anything else. There's a couple other ones, but without literally memorizing all of the possible charges that all of these guys can have, which is nuts. Like, I don't want to do that. You don't want to do that. I don't want to do that, right? So that's why we write the Roman numeral here, right? So we don't have to keep track of which ones always stay the same. Questions about that? All right. And then the questions there about the ides, right? So the IDE ending is only for anions, right? Which are always going to be non-metals. Sorry.
Cool. That I got. Thank you
Yeah.
so much.
No problem. Other questions about naming ions? How are we doing with that?
So but it's like when they get more complicated, like when it's a formula.
Yes. So let's
I'm
talk about
struggling with-
let's talk about naming compounds, right?
Yeah.
Cool. So we have ionic.
I think it's like what I'm struggling with the most is when it's already a compound and trying to reverse it
Uh-huh.
into the charges.
All right. So let me bring up the test, the practice test. So let's look at so you want to go from the chemical formula to the chemical name?
Yes. Yes.
Let's do number 41 from the practice test.
Perfect.
So we start off with these guy, right? So going from the chemical formula to the chemical name, right? What is the cation name?
Isn't that magnesium?
Mm-hmm. So if we were just naming the ion, it would be the magnesium ion, right? But when we put them into the ionic compound name, we get rid of the ion, right? So magnesium is going to be our first part. And then what's our anion name?
Phosphide.
Phosphide. Whoops. And that's it.
I guess I was struggling with the Roman numeral aspect of
We're gonna
it,
get to those.
like on B
Yeah.
and D.
Yeah, we're gonna go through. We're just gonna go through a bunch of them because I think that's the best way to figure them out, right? Is everybody comfortable with this guy though? I would say that's the easiest case, right? When you just have the main group guys. So then B, we have this guy. So what is our cation name?
Cobalt.
Cobalt. We know we're going to need a Roman numeral for this guy, right? Everybody all right with Y? Sadie, you cool with me?
Because it's a transition
Can we go
metal.
over that again, why?
So we find cobalt on the periodic table. Where is it?
And the transition metals.
Yes, and transition metals always have to have the charge given, right? So we know we're going to need a Roman numeral here. So let's talk about how to figure that out. But before we do that, what's the name of our anion?
Chloride.
right? And what's the charge on chloride?
-1.
And how many of them do you have?
1.
Two,
Sorry,
right?
2.
So you have -1, and there's 2 of them, right? So you have an overall charge of
-2.
-2, right? So what must the charge on cobalt be?
2.
2. Right? Does
Does
that
that just take the fact that there was a 2 there and use that, or does that not always work?
It doesn't always work. So it works in this case because the charge is a multiple of 1, right? But if you had like a -2 charge or a -3 charge, then it doesn't work.
But is it because CO didn't have anything that you could do that?
So let's look at some more examples, and I think we'll clear that up. Yeah. So these are all great questions. Transition metal compounds are the hardest ones, I think. So besides getting into polyatomic ions, which we'll talk a little bit about today, just so you know what not to worry about, but it's not going to be on the exam. Is it okay if I erase? I kind of already started, sorry. All right. So let's see. So let's look at C, because this one is a little bit weird in the answer key. So, looking at aluminum, right? That's one of those 3 weirdos that we talked about when you're going up the stairs. And it always has a +3 charge, okay?
You're not going to ask, are you going to ask us any questions with those few weird ones on it?
No. But just so you know, because the answer key is going to tell you one answer, right? Because this guy always has the same charge, this name is just going to be aluminum oxide, right? Now, if you were to put this, it would be fine, right? And let's talk about how to find that, because I think this is kind of tricky if you don't know that this is a +3 always, right? So, oxide has what charge?
-2,
-2. And how many of them are there?
3.
So you have a total of -6 coming from the oxides, right? So that means these 2 guys, right, must have a total charge of +6. Still with me? So if I want to know the charge on the individual aluminum, I divide it by the number of aluminums in the compound, and that tells me that it has a +3 charge. Okay? So, the key to being able to solve this kind of problem is knowing the charge of oxide. Right? If you don't know the charge of oxide, you're not going to be able to figure this one out, right? The other thing that I think some people were struggling with is making sure that you remember that subscripts are identifying the number of atoms or ions that you have in the compound, right? Whereas the superscripts are identifying charges. Where this gets especially confusing is when you're talking about polyatomic ions like nitrate, right? So the nitrate ion has 1 nitrogen, 3 oxygens, and an overall -1 charge, right? So that's when it usually gets more complicated, but again, understanding all of these components are how you hopefully get the full picture correct. Questions about aluminum oxide? Again, as Sadie pointed out, I will not give you one of the tricksters. Okay? So
I still don't understand how you got -6. Like I don't understand like the whole process of like how to find.
so this is my charge, right?
Mhm.
You okay with me, Helen?
Yeah.
And this is how many of them I have.
Mhm.
Let me do it pictorially for you, because I think it's helpful. Whoops, sorry. Off the map, right? This compound literally has all of these guys stuck together, right? Now, if you didn't know this, right, which presumably you didn't,
Yeah.
you have 3 oxide ions. Each one of them has a -2 charge, right? So -2 times 3 gives you a -6, right? Whatever your negative charge is, you must have an equivalent positive charge in order for this guy to be a neutral compound, which it always has to be. Neutral meaning no net charge. Does that make sense, Helen?
Mhm.
So if I know that all of my oxides give me a -6, then that means that all of my aluminums must give me a +6. If I know I have 2 of them, it means that the 6 positive charges are spread out over 2 aluminums, which means each one of these guys must be +3. Does that help, Helen?
Yeah, it kind of does.
So it needs to balance, basically.
Yep,
Right?
totes.
Gotta have balance.
Mm-hmm. Yeah. And let me see if I can find, I think there might be a simulation in the PhET world where you can take these different ions and literally stick them together. Because I honestly think the visual representation is really helpful. It's a pain in the ass to do for every single one of these. You don't want to do it, right? But it's just it's helpful in terms of seeing what you're actually dealing with, right? So, because I think the numbers kind of can get confusing if you don't know what everything is representing. But seeing this picture hopefully helps you understand why there's a total -6 charge, right? From the oxides rather.
Yeah, I kind of understand it through the picture more than the numbers.
Yeah, totally. But the key is eventually you have to be able to stick those things together, right? So, but if it helps you to visualize it, do it for sure.
Thank you.
Mm-hmm. Yeah, one of my colleagues actually for the Chem 152 lab made these cards where it's like oxygen, oxide ions, and then so aluminum would be +3. So it's like puzzle pieces where you can stick them together and see how many puzzle pieces you need to get them to completely line up with each other. And it's actually a super cool activity. It's probably the most fun way to know how to figure these out. And I know that's not saying a lot, but yeah. So there are really good visual representations that you can check out on the line that are better than just numbers. So,
I think you sent us one.
did I give you one? Okay, cool.
I think, yeah.
I don't remember. Oh, and the other thing too is a little bit of foreshadowing here for you guys, but the lab that we're starting, technically the lab that we're starting for most of the sections this week is the Nomenclature Lab, right? So that is going to have a lot of this and a lot of practice, right? So for the nomenclature, it's complicated to keep all of the different ways to name things in your head and all of the different ways of organizing this stuff. But when you practice that, it becomes second nature, right? So it really is very much like a language where if you practice it, it'll start being automatic, but if you don't practice it, then it will constantly be confusing. So, okay. Let's see. Let's do D and G. Okay, so for D, what's our cation name?
Cadmium.
Mm-hmm. And the anion name?
Sulfide?
Mm-hmm.
Let's say sulfur.
Right. And cadmium is a transition metal. So we need to have a Roman numeral next to it. What is the charge on cadmium here?
2,
Why?
because we have the sulfide is 2 minus, so you need 2 colors to balance.
So cadmium, because we know we only have one of them, right? That one cadmium must have a positive 2 charge in order to balance with the one sulfide, right? Boop. Does that make sense, guys?
Yes.
Bye, Priscilla. Now this one looks tricky, but it's actually pretty easy, right?
Potassium.
Potassium? Sorry, that was really bad. I can do better.
It's phosphide, right?
Yep.
Is that it? Because potassium or phosphide is negative
Oh,
3.
because it's like an ion.
Yeah, so because phosphide and potassium...
It's an anion.
Yes, so as an anion, it's always going to have an IDE here, right? But why we don't have to put a charge next to potassium is because potassium is
Metal.
in group 1, right? Which means its charge never changes. It's always positive 1, right? And phosphide is a negative 3 because it needs to gain 1, 2, 3 extra electrons to get to that noble gas electron configuration. Does that make sense, guys? Questions? I want to do Number 32, just since we didn't really get a whole lot of practice with that in the lecture. But I think it's pretty easy, so we can fly through it. So we're asked to give the Lewis dot structure for each of the following atoms, right? So with the Lewis dot structure, we write the chemical symbol, and then around it, we draw all of the valence electrons, right? So how many valence electrons does oxygen have?
6.
6. Right? Since you're not actually going to be drawing the dots, this may not be as important to you. But how you spread these guys out does not matter, right? So these two, as far as I'm concerned, would be equivalent. Okay? So how about carbon?
Four valence electrons.
4 valence electrons. Right? Anything giving you 4 dots around it? Questions about these?
Sorry, what?
Anything that gives you 4 dots.
Oh,
right?
Okay.
How about nitrogen?
5 valence electrons.
Right? Something like that. I got 5 dots around nitrogen. Argon.
Full 8.
It has 8 electrons, which is the maximum number of dots that you'll have. There are elements that have more valence electrons than that, but when we're talking about Lewis dots, we're generally talking about them in the context of covalent compounds, which we'll find out next week tend to only be nonmetals. Okay, so because they're only nonmetals, you're really only dealing with these guys, right? And so you're only dealing with that 8 maximum for the most part.
Professor, and how you got the valence electrons is because of the number of the atomic number 18. You subtract that from 10, which is neon, to get the 8.
Yes, that's one way of doing it. The other way that you could do it is we could just count across, right? 1, 2, 3, 4, 5, 6, 7, 8 electrons.
Okay.
Right?
Okay.
So for oxygen, 1, 2, 3, 4, 5, 6. Right? Whatever makes more sense to you. Yeah. Easy peasy? Let's do a couple examples from number 40. Since, again, oops, not 41. This is the one that I think we spent the least amount of time with. So, this question is asking how many of each ion would be required to make an ionic compound? right? And part of the key to this question is knowing that ionic compound is code for neutral charge, right? So you know whatever the charges are, they have to sum to 0. So, how many of each of these ions am I going to need to make a neutral ionic compound?
You'll need 3 cations and 1 anion.
You will, exactly, right? So you're going to need 3 of these guys for every 1 of these guys. And then the chemical formula would be so this number is going to come down here, right? That's how many cations we need. And then we don't write the 1, it's implied. Okay? Now, if you can't see this in your head, that's okay. There's a systematic way that you can approach this, right? So let's say we started off with 1 of each. Uh-oh. We're going to come back to life.